So this week we're going to be looking at energy. Energy is one of the most important concepts we're going to be dealing with this year because it applies to all areas of physics, it applies in chemistry, biology, and all branches of science and engineering. So what is this term energy? I'd like you to realize that the term energy actually goes back to ancient Greece. Their concept is not the same as our modern idea of energy, but that's where the roots stretch back to. Our modern idea of energy can be traced to James Prescott Joule. In fact, his insights in energy were so profound that the unit of energy is now known as joules. Okay, so James Prescott Joule, modern idea of energy. As I was mentioning, energy is important in all areas because there are so many different types of energy. So here's a partial list of some of the most important types. We have kinetic, gravitational, elastic, nuclear, chemical, light energy, solar energy, where light energy turns into electricity. We have sound energy, thermal energy, heat energy. We have electrical energy and we have magnetic energy. So lots of different types in lots of different areas of life. All of these energies should be measured in joules. But what is it? What is our modern idea of energy? I think a nice, easy way to think about energy is it's a measure of an object's ability to bring about changes to itself or to other objects. So if I possess energy, I can bring about change. Energy creates change. So here we have Chris, who's going to give energy to a bowling ball. And the bowling ball is going to use that energy to change things about the pins or the environment around the bowling ball. When we again look up close, we can see that the bowling ball brought about changes to the pins and to the environment around the pins by making a noise. Okay, so what kind of change can energy create? It can change speed, height, shape, temperature, phase, chemical composition. Energy could take a water molecule and break it up into hydrogen and oxygen. It can change brightness, loudness, voltage. It can change the magnetic properties of an object. So energy can bring about all kinds of different changes. Without energy, we cannot have change. Okay, so a little bit of vocabulary. This term work. I want to make sure you understand what work means. Not in the concept of I'm working at Walmart or Target or any of those other terrible stores. We're talking about what do we mean scientifically by the term work. Work is the energy added to or removed from an object. You find the work by taking the force that you're applying to the object and multiplying by the displacement while that force was being applied. Okay, so it's force times displacement. That work is energy added to the object. We measure it in joules. In this case, the energy causes a motion to take place. It takes the cart and it makes it move. It doesn't necessarily have to give an object speed. So for instance, when I apply a force to these elastic bands, I give energy to the bands, and now there is energy stored inside of these bands. Notice right now, even though I'm applying a force, I am no longer adding energy. The energy is the same now as it is now because there's no delta X. So once you stop increasing your delta X, you stop giving the object energy. All right, so it's force times displacement. Let's do a calculation where we make the object move and gain speed. So you can see the fire extinguisher has a force of 155 It shut off after it traveled 30 meters, and you just take the force times the displacement to get your energy. That energy will be measured in joules. Oftentimes your energies will come out really big, so in this case you're going to be in the thousands. So you could say we created such and such kilojoules worth of energy. It might be megajoules, gigajoules, so be ready to use your metric prefixes. I want to take a moment to make sure you understand the connection between the work and the direction of the force relative to the direction of motion. So watch this and make sure you understand it. In case number one, our force is going to be with the object's original motion. So if you watch, he's moving to the left. When he hits the red line, we're going to apply a force to him, also to the left. And it's going to cause him to speed up. So if the force is in the direction of motion, he gains energy. If the force and displacement are in the same direction, you gain energy. In this case, we're going to have the force in the opposite, 180 degrees out of line with the direction of the motion. So he's moving to the left, the force is to the right. Now the force does not add energy, the force removes energy. So when the force is with you, you gain energy. When the force is against you, you lose energy. Finally, if the force is perpendicular to the way you're trying to move, you don't do either. That object is not gaining or losing energy, even though there's a force on it, even though it's moving. Since they are perpendicular to each other, it is not gaining energy. There is no work being done. It is not getting faster or slower. So it has no more energy now than it does now. It's going to move at a constant speed. So the work formula is often written like this. Work equals force parallel delta x. That reminds you that the force either has to be perfectly in line with your motion or perfectly against your motion. Perpendicular forces do not add energy. Okay, that takes us to our second term for today, and that's the term power. Power depends on energy. Power tells how much energy you're adding or removing in 1 second. Okay, so when I say what is power, it's the energy added per second. The unit for power is going to be watts, named after James Watt, who was one of the people who tried to measure the power of things like steam engines. The formula to calculate power, power equals work over time. Remember, work is energy added to an object. So it's energy added per second. That's your power. It's the joules per second. And that's called watts. Be careful. This W as a variable means work. This W is a unit. It means watts. So if you had, for instance, 100 joules in 10 seconds, that would work out to 10 watts, 10 joules per second. It might be easier to write it like this, although not many people do for some reason. Power equals the change in energy divided by time. You take the change in energy, you see how much time that took, and together that will give you your power. I want you to know some typical powers. So a light bulb would be between 10 watts and 100 watts. The higher the wattage, the more energy that's coming off of that light bulb. A microwave might range from 800 watts to 1500 watts. Again, the higher power means it's going to cook faster. It's got more energy added to your food. Who microwave pizza per second. Then we've got an electric car that has a power somewhere between 400 and 800 kilowatts. Okay, the higher power means it can add more energy per second. And finally, your phone charger might range between 5 watts and 20 watts. The 20 watts would charge your phone quicker because it's adding more energy per second. Okay, so power tells you energy per second. Please make sure you know some of these typical powers so you have an idea of what kind of numbers you should get for your power problems. Before we end for today, I just want to remind you of your metric prefixes. So if you have 5 kilowatts, that means 5,000 joules per second. Kilo means 1,000. If you have 10 megawatts, that means million. Mega means million. 10 million joules per second. You might even have gigawatts. Okay, so 8 gigawatts would mean 8 billion joules every second. Sometimes you might even have things that are very low powered, and they might be milliwatts. Remember, that's thousandth of a watt. So that would be 10 divided by 1,000 joules per second. Okay, so anyway, that is energy and power. Hopefully you understood what we talked about, because they're very important ideas that we'll be using off and on all year and in all other areas of science.